This is a video recording of describing motion along a line, which is speed and acceleration in simple terms. Let's just recap the difference between distance and displacement. We've got 2 points here, A and B, and if we follow this line along here, we go a total distance. And that's measured in meters. So for example, the distance could be 200 meters, and that is scalar, just got a magnitude only. A to B, we've got a direction to the east. So let's say that distance is 100 meters to the east. It's now a displacement. It is a vector. Remember, vectors have got magnitude and direction. So the difference between distance and displacement is important in this topic in physics. You need to know various different speeds, typical values of speed. So a person walking is at 1.5 meters per second, a person running is at 3 meters per second, and a person riding a bike is at 6 meters per second. If you look carefully, the numbers double each time, so there's a pattern involved. You also need to know that the speed of sound is 330 meters per second. Cars typically move at approximately 20 meters per second. Trains move at approximately 50 meters per second, and planes move at approximately 250 meters per second. You would need to be able to recognize or estimate these numbers. To calculate speed, we use the equation speed equals distance divided by time. Distance is measured in meters, time is measured in seconds, so meters per second is our unit for speed, meters per second. And the equipment we'd need to calculate speed, distance, we'd either need a ruler or a trundle wheel to get the distance, and time we'd need a timer or stopwatch. So for example, 10 seconds. We can represent speed on a distance time graph, and that shows us how far objects move in a certain amount of time. So here's a distance time graph. We can tell it's a distance time graph by having distance on the y-axis, time on the x-axis, and we've got 4 very unique areas of this graph. We've got A, B, C and D. A is a straight line going up, and a straight line in physics tells us it is constant. So A is a constant speed. B, the distance is not changing, it's staying at 50. So it is stationary, it is not moving. C, the line is getting steeper and steeper and steeper, so it's getting faster and faster and faster, so it is accelerating. And accelerating means getting faster. And D, the distance is going back, so it's returning to the start of the journey. Return to the start of the journey. And we can calculate speed using distance time graphs using the data. So if I want to find the speed at this point here, which is labelled x, I go across and get my distance of 50 meters. I go down to get my time at 10 seconds. 50 meters divided by 10 seconds equals 5 meters per second. So you can use the data on the graphs to get a speed. The rest of the video will be for foundation students as well, but this little bit here is just for higher tier students. If you're asked to calculate the speed from a curve, so it's increasing like this, so if you're asked to find the speed at this point here, you calculate the gradient, which is the change in y divided by the change in x, and that gives you your speed. So that is something to bear in mind, that you can calculate the speed from a curve using a gradient. So now we know the difference between speed, distance and displacement. We now need to know what acceleration is. An acceleration, the letters A, is the change in velocity. Triangle in physics, the delta, means change. V stands for velocity. T stands for time. And A stands for acceleration. So the change in velocity divided by time. I'll do a worked example in a minute. The units for velocity is meters per second. The unit for time is seconds. So meters per second divided by second, we end up with meters per second squared. And that squared is a really big clue in a question that it's an acceleration they've given you. So let's do a worked example. I've got an object that's travelling at 5 meters per second and it goes to 25 meters per second in a space of 10 seconds. So how do I work this out? So I'm going to represent this now. So first of all, I do my change in velocity. My change in velocity is 25 take away 5, which equals 20 meters per second. I can now substitute these numbers into my equation above. Acceleration is the change in velocity divided by time. My change in velocity is 20. My time is 10 seconds. 20 divided by 10 equals 2 meters per second squared. Do not forget the squared when doing the units for acceleration. Let's look at a different acceleration. I'm starting at 50 meters per second and I'm decelerating to 0 meters per second. So my change in velocity is 50 take away 0, which equals 50 meters per second. Or you could do 0 minus 50 and get minus 50. It doesn't matter, I'll explain why in a second. So now we do our equation. Acceleration is change in velocity divided by time. Change in velocity is 50. The time was 2.5. So now I use my calculator. 50 divided by 2.5 gives me 20. 20 meters per second squared. If I'd use my minus 50 meters per second, I'll show you that I get exactly the same magnitude, and all that happens that's different is I get a minus at the end. And that minus 20 meters per second is absolutely correct. That minus just tells us it's decelerating. That's all it's telling us. We can plot acceleration on velocity time graphs. Velocity time graphs, velocity is on the y-axis, measured in meters per second. Time is on the x-axis, measured in seconds. And again, I've drawn the same shape graph, but this time A, B, C and D mean different things because it's a velocity time graph, not a distance time graph. The velocity is increasing, so it started at 0 and the velocity is increased, so it is accelerating. B, this time the velocity is not changing, so it's constant velocity. It is not stationary, constant velocity. C, the gradient is getting steeper and steeper and steeper, so it's increasing acceleration. And D, the velocity is decreasing, so it is deceleration. Or you could call it negative acceleration. Both are absolutely correct. Remember, acceleration is a vector, so negative just means in the opposite direction. Again, we can use data on our graph to calculate. So let's say the point here is 0 and the point here is at 20 meters per second. Let's say it took 10 seconds to do that. We get our data off our graph. Acceleration is our change in velocity divided by time. Our change in velocity has gone from 0 to 20, so our change in velocity is 20. The time it took to do that was 10 seconds, so that is 2 meters per second squared. This little bit is for higher tier students only. Foundation students stay with us because they're a little bit more for you. On velocity time graphs, we can calculate the distance travelled by getting the area under the graph. And you can see here I've broken it down into a triangle and a rectangle. So distance is the area under graph. My triangle here, my base is 0 to 10, so my base is 10. My height is from 0 up to 5, so the triangle is base times height divided by 2, which is 10 times 5 divided by 2. Use a calculator to make sure we don't make any mistakes. 10 times 5 divided by 2, which equals 25 metres. So in that triangle proportion of the graph, the object has travelled 25 metres. In the rectangle, it started at 10 and gone to 40. And the area for rectangle is base times height. So the base is 40 take away 10, which equals 30. And the height is 0 up to 5. So it's 30 times 5, because base times height equals 30 times 5. As always, use our calculator. Make sure we don't make any mistakes. Equals 150. So we now need to add that 25 plus the 150, which gives us 175 metres. So in that area under the graph, the object has travelled 175 metres. There's a more complicated equation, more complex equation to calculate acceleration, and it's the v squared minus u squared equals 2 times a times s. And the v stands for the final velocity. The u stands for the initial velocity. The 2 is just a number 2. The a stands for acceleration. Same units as before, meters per second squared. And s isn't speed, s is distance. And distance is measured in meters. So let's do a worked example of this. Starting from 3 meters per second, underline number, accelerating at 0.5 meters per second squared for a distance of 200 meters. Calculate the final speed. So I'm trying to get v, not v squared. People always forget the squared. So the first thing I do is write the equation. Make sure not to forget the squared. Now I substitute the numbers in. Well, I don't have v, I don't have the final velocity, so I'm going to put v squared again, minus follows through, u. So what was my starting speed? So look at my question, I'm starting at 3, but I've got to have the squared, and that equals 2 times my acceleration of 0.5 times my distance of 200. And before I do anything else, I'm going to simplify this. So v squared minus, and 3 squared is 9, and 2 times 0.5 times 200, I'm going to simplify that to make my life easier. 2 times 0.5 times 200, which happens to work out as 200. I want to get this v squared term on its own, so I need to do the opposite of minus 9. The opposite of minus 9 is plus 9, so if I plus 9 to this side, I get rid of the minus 9, and I plus it to that side. So v squared equals 200 plus 9, which is 209. But I'm not interested in v squared, I'm interested in what v is. So to get rid of the squared, I need to do the opposite of squared, which is the square root. And my number was 209, so I square root 209. So v equals square root of 209 again. Use a calculator. 14.4568. And again, If I'm in doubt of how many significant figures to put, I write my whole calculator screen down. Velocity is measured in meters per second. You could be asked to use this equation to find the initial velocity, to find the acceleration, or to find the distance. The key thing is to recognise any question with acceleration and distance, you have to use this equation. This equation you do not need to remember, it will always be given to you on an equation sheet. Always underline numbers in the question, always substitute into the equation, not forgetting the squares, then simplify, then rearrange, take a square root if you need to. That's my advice for v squared minus u squared equation. The final thing you need to do for describing motion in this line is falling objects in a fluid. And remember, we mean liquid or gas for fluid, not just liquids. So I'm going to start off by drawing a simple scenario. This could be an object falling through the liquid or falling through the air. I'm just going to have it as a ball, but I'm going to draw it as a free body diagram. Could be a penny, could be anything. So we've got an object and we drop it. At the point of it being dropped, that object has only got weight. It's only got weight. The resultant force is downwards, so it's accelerating downwards. But as it accelerates downwards, it gets faster and faster and faster. It's accelerating, so we get some air resistance, or we get some water resistance, or fluid resistance. So we call that drag, and that drag increases as it gets faster. So it's still accelerating, because the resultant force is still downwards, because we got this magnitude, take away that magnitude, we still have a resultant force down. So it's accelerating, but the acceleration is decreasing. It's getting faster, but not as much as it was. Eventually, as it gets faster and faster and faster, the drag will equal the weight. So the resultant force is 0 newtons, and then it'll be at terminal velocity, or top speed. So for a more common example of something reaching a top speed, we can think about someone running or a car accelerating. So now I'm going to draw an example of a car accelerating to get top speed. So here we've got a car, and let's give it a thrust of 500 newtons. At that point, initial acceleration, there's no drag, there's no air resistance, so the resultant force is forward, so the car is accelerating, getting faster and faster. But as the car gets faster, and faster, the drag increases. So we start off with a little bit of drag, let's say 50 newtons. 500 take away 50 equals 400 newtons forwards. It's still accelerating, but it has decreased. The acceleration has decreased. And eventually, as it's accelerating it faster and faster and faster and faster, eventually what will happen is that the drag and the thrust will be equal, and at this point we've got 0 newtons of resultant force, so we've got terminal velocity, which you may hear as top speed. We can represent both these scenarios on a velocity time graph. So if I draw the velocity time graph here, velocity in meters per second on the y-axis, time in seconds on the x-axis. So what's happening at the first point in both situations? We've got the maximum acceleration, so we've got the steepest acceleration. So let's label these up as option 1, option 1. So steepest acceleration. At that point we get some drag, whether it's drag from air resistance or drag from fluid resistance, it doesn't matter. So what this does, it makes the acceleration decrease. So it starts to curl, starts to plateau. So it's still accelerating, the velocity is still increasing, but just not as much, the gradient's getting shallower. And then eventually at point 3, the drag and the weight are equal when it's falling, or the drag and the thrust are equal for an object or vehicle or person running or person swimming. They will equal out, so it'll be perfectly horizontal. The velocity is not changing, it is at constant speed. And this is for physics only, this next bit. We could have parachutists. This is where everything comes together. So if we have a parachutist, they start off by jumping out of a plane or from a high place, and at that instantaneous point, they've only got their weight. They've only got their weight, so we've got max acceleration. So I'll leave that as max acceleration. As it accelerates, the drag, the air resistance, increases. So the acceleration decreases. It decreases up until a point where the drag and the weight are equal. So we've now got terminal velocity, which I'm just going to label up as TV to save some space. But it's a parachutist. What a parachutist does then is opens a parachute, which increases the drag, massively increases the drag. So we've now got our resultant force upwards. The weight is still stayed constant, we've got a resultant force upwards, and this slows a parachutist down. When you see a video of a parachute, it looks like they're flying up. They're not flying up, they're just slowing down. So deceleration, it's slowing it down. But as they're decelerating, the drag gets lower and lower and lower and lower. So the drag's decreased. So what happens is the deceleration decreases. So they're getting slower, but by less and less and less and less. And then eventually, the drag will balance out with the weight. So we get a second terminal velocity. Let's call it terminal velocity 2. And we can represent this on a velocity time graph. Velocity on the y-axis, measured in meters per second. Time on the x-axis, measured in seconds. So we have maximum acceleration to start with, so the steepest line to start with at point 1. Then the acceleration slows down, point 2, so it starts to plateau until we reach terminal velocity, point 3. At this point we open the parachute and we get a massive deceleration, so the velocity decreases rapidly. At point 5 the deceleration starts to lower, so it starts to curve, and then at point 6 we've got a terminal velocity. Then the very last thing that happens in a parachutist is they reach the ground, so the velocity is 0. So the velocity suddenly goes to 0, reach ground, so 0 meters per second. And it's at this point here, with a massive decrease in the meters per second, the massive decrease in velocity, where the parachute is opened. And that is everything about motion in a line. If you need to, watch it back, look at the bits that are foundation only, look at the bits that are higher tier only, and remember this parachutist section is for triple physicists only.